Welcome back. Once again, I am Professor and I'm happy to be your tutor. Now, just to refresh your mind on our progress so far, we started from the universe and zeroed in on matter. I said that for our course, we are only interested in the solid state of matter, so we won't pay any attention to the other states. Then we zoomed into the building blocks of matter, which are the atoms. We learned that the atom has two regions. There is the central nucleus, which contains protons and neutrons, and there is the area around the nucleus where we can locate an electron. The protons and the neutrons, however, do not play any role in electronics. Hence, our focus will be on the electrons in the atom. We have also learned about shells. We said electrons move around the nucleus at certain specific distances called shells. These shells are the various energy levels an electron can occupy. Within the shells, electrons are grouped into subshells, and within the subshell, the electrons are actually located in what we call orbitals. Also, shells that are closer to the nucleus tend to have lower energies, and the farther away a shell is from the nucleus, the larger it is, the more electrons it can hold, and the electrons in this shell tend to have higher energies. Also, we learned that the outermost shell is called the valence shell, and the electrons found in an outermost shell are called valence electrons. In electronics, only the valence electrons play a role. Hence, the electrons that we are interested in are the valence electrons. Now, to add to it, there are other applications that depend on the core electrons. For instance, in the production of X-ray, an electron in the K or the L shell could be targeted. However, that is not part of our business, so let's move on. Now, just a reminder, we are still on course to answer the question, how does the light bulb work, and also build a solid foundation for electronic systems design. All right, let's get started. In this lecture, we will learn about the periodic table and how electrons are arranged or distributed in the shells of atoms. In the previous lecture, I said that there are about 118 known elements. 94 of these elements exist in nature, and the rest were created in the lab. For easy reference, scientists have actually arranged these elements in a tabular form called the periodic table. So the periodic table actually summarizes the properties of the known element. Whenever you need information on any element, chances are that you can actually find it in the periodic table. Let's look at the periodic table. There is an online resource designed by the Royal Society of Chemistry that I love so much. You can check it out using this URL. In a modern periodic table, elements are listed in order of increasing atomic numbers, and they are also organized in rows and columns. So, a row in the periodic table is called a period. In total, there are seven numbered periods labeled periods 1, 2, 3, 4, 5, 6, and 7. There are two special series of elements that are embedded in period 6 and period 7. They are the lanthanides and the actinides. Lanthanides are also known as the rare earth elements, and they are embedded in the sixth period between barium and hafnium. To make it easy to display the whole periodic table, lanthanides are usually shown as a separate row below the rest of the periodic table. Actinides are also embedded in the seventh period between radium and rutherfordium. Like lanthanides, they are also usually shown in a separate row beneath the rest of the periodic table. And on a typical periodic table, you find them right beneath the lanthanides. Elements are also arranged in groups. Now, Elements in the same group have similar physical and chemical properties. This is because most of the chemical properties of elements depend on the orbital that holds the valence electron. So, in a nutshell, the periodic table is actually a quick way to refer to information about a particular element. Information such as the atomic mass, atomic number, and chemical symbol can be obtained easily from the periodic table just by inspection. For instance, elements in the same period have the same number of shells, and the number of shells is actually equal to the period number. So, elements in period 1, for instance, have only one shell. Elements in period 2 have two shells. Period 3 have three shells, in that order. Also, in a period, each next element has one more proton and is less metallic than the previous element. Another useful information that you can get from the periodic table is the location of the valence electron of an atom of a particular element. There are also some trends in element properties that can be discerned from the periodic table. This includes things like electronegativity, atomic radius, ionization energy, and many more. Now, I will throw more photons on this in the next lecture. Apart from the periods and the groups, the periodic table also has another type of grouping called blocks. A block is actually a grouping based on the location of the valence electrons of atoms of the element. So that means that all elements whose atoms have their valence electrons in an s orbital would be found in the s block. Elements with valence electrons in the p orbital will be found in the p block. Those with valence electrons in the d orbital will be found in the d block. And finally, elements with their valence electrons in an f orbital would be found in the f block. Now, an element may be a metal, non-metal, or metalloid. There are, however, some elements that have not yet been classified. Metalloids are elements that have properties between metals and non-metals. For example, boron, silicon, and germanium. There is actually more to be said about the periodic table, but that is actually beyond the interest of this course. Now, let us look at how electrons are arranged or distributed in the shells of the atoms of these elements. To arrange the electrons in shells, you need to know some rules. Details of this are in the subject of chemistry. However, we will look at a few that are relevant to our course. The first rule is knowing how many electrons can fill a particular shell. In the previous lecture, I said that each shell has a number of electrons it can hold, and this is given by the relation 2n squared, where n is the principal quantum number of the shell. Also, each shell has one or more subshells, and the number of subshells is equal to the principal quantum number of that shell. The subshells contain orbitals, and orbitals can hold up to 2 electrons, but they have to have opposite spin. That's according to Pauli's exclusion principle. So, for instance, the first shell has a principal quantum number of 1. Therefore, it has only one subshell, and that is the S subshell. The s subshell contains only one orbital called the 1s orbital. Therefore, the first shell can hold only 2 electrons. The second shell has a principal quantum number of 2. This means that it has two subshells, which are the 2s and 2p subshells. The p subshell, however, has 3 orbitals labeled px, py, and pz, each of which can hold a maximum of 2 electrons, making a total of 6 electrons. Therefore, the second shell can hold up to 8 electrons. Using this method and this table as a guide, I want you to try and calculate the number of electrons that can be contained in the m and the n shells respectively. Rule number 2 is about the order in which electrons are arranged in the orbitals. I said in the previous lecture that electrons first fill shells with lower energies before those with higher energies. That's according to the Hubble principle. So the order of filling orbitals is as follows. But before that, take note of the notation used. Each subshell is preceded by the quantum number of the main shell. The number of electrons in the subshell is written as a right superscript. Now, the order in which electrons fill the orbitals is as shown in this diagram. Take note, however, that this arrangement is done assuming that the atom is in its ground state. When we say that the atom is in the ground state, it means that it is in the lowest possible energy level that it can occupy. So take it as the calmest an atom can be. One thing that you should take note is that the 3d orbitals actually comes before the 4s orbital. However, in filling shells with electrons, you must fill the 4s orbital before the 3d orbital. This is because the 4s orbital has lower energy than the 3d orbitals. However, when you are writing the electron configuration, you have to write the 3d subshell first before the 4s. So as an example, let us look at how to arrange electrons in the following element. And we are going to look at hydrogen, helium, carbon, neon, aluminum, silicon, argon, and copper. Let's start with hydrogen. Hydrogen is the first element in the periodic table, hence it has an atomic number of 1. This also means that it has only one proton. And since the number of electrons in an atom is equal to the number of protons, hydrogen atom has only one electron. So applying the rules, we will put the electron in the first shell. Now, since the hydrogen atom has only one electron, it means that it is only the 1s orbital that will receive an electron. Helium is the second element in the periodic table, hence its atomic number is 2. Now, this means that it has 2 protons and 2 electrons. So applying the rule, we put all 2 electrons in the 1s orbital. However, according to Pauli's exclusion principle, we have to arrange them in opposite directions. By supplying the 2 electrons, we fully fill the K shell because the K shell can take a maximum of 2 electrons. Continuing, let's look at that of carbon. Carbon is the 6th element in the periodic table, hence its atomic number is 6. Also, this means that it has 6 protons and 6 electrons. Therefore, applying the rules, we have to put 2 electrons in the 1s orbital. Since that fails the first shell, we must move to the second shell. The second shell, as we know, has a principal quantum number of 2. Hence, it contains 2 subshells, which are the 2s and 2p subshells. 2s has only one orbital. The 2p, however, has 3 orbitals, each of which can contain 2 electrons. So, after filling the K shell with 2 electrons, we will be left with only 4 electrons. Out of these 4 electrons, we will first fill the 2s orbital with 2 electrons, and then the rest of the electrons will be put inside the 2p orbitals. Now, let me mention that subshells like p, which have more than one orbital, are said to be degenerate. Degenerate orbitals are more stable when half filled. Okay, so in filling degenerate orbitals, you must first put one electron into each of the orbital before pairing them up if you happen to have more electrons. Neon is the 10th element. So as usual, its atomic number is 10. This means that it has 10 protons and 10 electrons. Now, resuming from where we left off with carbon, we now have enough electrons to fill the 2p subshell. Filling the 2p subshell means that the second shell, which also happens to be the valence shell of neon, gets filled up. Aluminium is the 13th element. That means that after neon, we will have 3 more electrons to arrange. Since the L shell is full, we must move to the next shell, which is the M shell. The M shell has a quantum number of 3. Hence, it contains 3 subshells, which are the 3s, 3p, and 3d. The M shell can take a total of 18 electrons. So continuing from neon, we will put 2 electrons in the 3s orbital, then 1 electron in the 3p subshell. We will do the same for silicon, which is the 14th element. For silicon, there will be 2 electrons in the 3p subshell. Argon is the 18th element. So resuming from silicon, argon has enough electrons to fill up the 3p orbitals. Copper is the 29th element. Hence, it has an atomic number of 29. This means that it has 29 protons and 29 electrons. Because the M shell can hold up to 18 electrons, it means that we still have orbitals in the M shell to contain these electrons. From argon, there are 11 more electrons to arrange. Now, recall that the 4s orbital has a lower energy than the 3d orbital. So, we will have to fill the 4s orbital first. This leaves us with 9 more electrons. The 3d subshell can take a total of 10 electrons. Like the p subshell, the 3d orbitals are also degenerate. So we will put the rest of the electrons in the d subshell by first half filling them and then pairing them up. Now, I want you to take note of this and also the electron configuration of copper. We will come back to it in another lecture. Elements in the D block like copper and iron are called transition metals or transition elements. These elements actually have certain interesting characteristics that we will explore later. A typical example is their ability to have more than one stable electron configuration. There is a group of elements called the main or representative element. These elements are in the S and the P blocks. The reason they are of interest is that they are the most abundant elements on Earth, in our solar system, and even in the universe as a whole. Now, these main group of representative elements are also assigned special group names, and usually on periodic tables you see things like 1A, group 1A, group 2A, group 3A, up to group 8A. Okay, this grouping is specifically for this main group of representative elements. One important property of this main group of representative elements is that they tend to bond in such a way that each atom has 8 electrons and 8 valence shell. Now, this actually results in a very stable electron configuration like as we have in the elements in group 18. This is what we call the octet rule. The rule is especially applicable to carbon, nitrogen, oxygen, and the halogen. Anyway, halogens refer to group 17 or group 7A elements, such as chlorine. However, the octet rule only applies to elements in the S and P blocks. A similar rule called the duplet rule exists for hydrogen and helium. There is also the 18 electron rule for the transition metals, but we will not talk much about that. Now, coming back to the octet rule, when the octet rule applies, we can write the electron configuration of those elements in a different way. With the octet rule, the first shell takes a maximum of 2 electrons, and aside that, all other shells take a maximum of 8 electrons. For example, the electron configuration of carbon, which is the 6th element, will be 2 6. Neon, which is the 10th element, would be 2 8. Aluminium will be 283. Silicon will be 284. Chlorine with atomic number 17 will be 287. Argon will be 288. Calcium will be 2882. That is according to the octet rule. Take note, however, that the octet rule only applies to S and P block elements. When the octet rule applies, elements with fully filled valence shells, according to the octet and duplet rules, are called noble gases. These noble gases are usually found in group 18 or group 8A of the periodic table, and they exist in nature as monoatomic gases. If you are interested in what a monoatomic gas is, just get any chemistry textbook. So in summary, the octet rule says that atoms of elements that obey the octet rule are most stable when they have 8 electrons in their valence shell. That is when they have the electron configuration of a noble gas. Now, because of this, atoms of these elements actually try to gain or lose electrons until they have the electron configuration of a noble gas. So through this process, an atom gains a net charge. An atom that has a net charge is called an ion. And in the upcoming lecture, we will look at how an atom can gain a net charge. Once again, let me remind you that we are still gradually building a foundation to make us good electronic system designers. Now, to be good at electronic system design, in my opinion, you need to understand these fundamentals. And I will urge you not to be in a hurry to jump into building circuits, okay? There are relevant things that you need to know first. That is why I'm taking some time to talk about these fundamentals, because I believe that if you can manipulate the building blocks, you can build anything, okay? Mostly to be innovative depends on your fundamental understanding. All right, that is all for this lecture. Thank you for watching.